everything in the universe obeys the laws of physics. So you'd think the laws would be pretty obvious. You want to know the laws of motion? Just look around, see how things are moving. But of course, that's not how it works. The laws of motion are not obvious or intuitive. They need to be learned with difficulty in school. And they needed to be discovered through careful experiments and insightful reasoning. For example, Newton's first law of motion says an object in motion will keep moving in a straight line at a constant speed forever, unless acted upon by an outside force. But when you throw a ball, it doesn't go in a straight line. It goes up and falls down. When you push on a wagon, it doesn't keep rolling forever. It slows to a stop. It takes a lot of work to keep something moving in a straight line at a constant speed. One reason is that we live on a planet where there's always an outside force, namely the Earth's gravitational pull. Even worse, we're embedded in a fluid, air, that resists the motion of objects. And there's friction between any two surfaces, like a wagon wheel and the ground. So it takes real imagination to figure out what would happen if there were no air resistance and no friction. How did Newton or anybody ever figure that stuff out? Well, in physics class, we learn by watching carefully contrived physics demonstrations. We watch plastic discs slide across an air hockey table with very little friction. We pump all the air out of a chamber to show that a bowling ball and a feather fall with the same acceleration. Well, Mother Nature provides us with a physics demonstration that's visible to everyone all the time. I'm talking about the motion of the planets in the sky. To the naked eye, the planets of the solar system are points of light that move from night to night relative to the fixed background of stars. In fact, the name planet comes from an ancient Greek word for wanderer because the planets wander through the constellations. And it was this celestial physics demonstration that led Newton to his law of gravity. The planets move in response to the sun's gravity without any friction. And each one is at a different distance from the sun. So by observing them, you can work out how gravity depends on distance. Our goal in this lecture and the next is to solve this physics problem in the sky. I want to dwell on this subject for 2 lectures and go into more mathematical detail than will be typical in this course, not only because it's fascinating, but also because we're going to encounter important concepts that will turn up repeatedly. Angular momentum, scaling relations, how to measure the masses of not just planets, but also stars and galaxies. We'll begin with the 17th century astronomer Johannes Kepler, who pointed out 3 patterns in the motion of the planets. They're called Kepler's laws. Kepler's first law is that the planets trace out ellipses as they go around the sun. The orbits look like circles, but they're not. They're slightly flattened into ovals. Take Mars's orbit, for example. It sure looks circular, but along one direction, the diameter is 0.5% larger than in the perpendicular direction. Easier to notice is that the sun is off-center. That's true for all the planets. The orbits are ellipses, and the sun is not at the center. It seems kind of needlessly complicated. Wouldn't it be simpler if the orbits were just circles? The ancient Greeks certainly thought so. And later, even when the data got better and proved to be inconsistent with circular motion, theoreticians didn't abandon circles. They doubled down on circles. They had the planets move in circles, the centers of which were themselves moving in circles. These are the epicycles that became the basis for the Ptolemaic model for the solar system, which prevailed up until Kepler. But the orbits are not circles, and they're not circles within circles, and it's our job to figure out why. But before getting to the physics of why the orbits are ellipses, we need to understand the geometry of ellipses. Let's start simple, though, with a circle. Mathematically, a circle is defined as the set of all points that are the same distance from some chosen center. Put a pin in a corkboard, then take a piece of string and tie both ends to the pin, making a loop. Then put a pen in the loop, stretch the string tight, and sweep around the board, drawing as you go. You just made a circle centered on the pin. For an ellipse, you need 2 pins, and you tie the ends of the string to the pins with some slack. Then stretch the string tight with the pen and sweep around the board, drawing as you go. What you get in that case is an ellipse. The 2 pins are the focus points, or foci, of the ellipse. For all the points on the ellipse, the distance to the first focus plus the distance to the second focus is a constant. That's the length of the string in our construction. The length of that string is also equal to the length of the long axis of the ellipse, the major axis. You can see that by pulling the pen all the way to one end of the major axis. The string now reaches from the far focus to the end of the ellipse and then back to the near focus. The only part of the major axis it doesn't span is from the far focus to the other side of the major axis. But that distance is exactly the same as the section of string that's doubled up on the near side. So if we unpinned the string and straightened it out, it would reach exactly across the major axis. We conclude that for any point on an ellipse, the distance to one focus plus the distance to the other focus equals the length of the major axis. To make a circle, we only needed to make one choice, the radius, which we'll call A. For an ellipse, the equivalent is the radius along the major axis, which we'll also label A, and we'll call that the semi-major axis. But with an ellipse, we also have to choose the distance between the center and either focus. We can choose whatever distance we want, as long as it's smaller than A. Tradition dictates that we express that distance as A times E, where E is a number smaller than 1, which is called the eccentricity. When E is 0, the foci coincide at the center, and we go back to a circle of radius A. And as E gets larger and closer to 1, the foci separate, and we get a more elongated ellipse. We need a couple more pieces of ellipse math before we're ready for the astrophysics. First is the area of an ellipse. For a circle, we know the area equals pi a squared. For an ellipse, it turns out to be pi a squared times the square root of 1 minus e squared. I won't prove that here, but it is a fun problem for those of you who enjoy calculus. Second, we need the mathematical equation for an ellipse in polar coordinates, and this one we will do together. We'll start by introducing a coordinate system. We'll put the origin at one of the foci, say the one on the right, and we'll lay down x and y axes along the major and minor axes. To specify the points on the ellipse, we could use x and y, but sometimes it's better to use polar coordinates. R is the distance from the origin, and theta is the angle measured counterclockwise from the x-axis. The question is, what is the equation for r as a function of theta? First, let's think about what we expect. It's going to be a rising and falling function. For theta equals 0, r has its minimum value of a minus ae. That's a times 1 minus e. As we dial theta up to higher values, r increases. And at theta equals pi, 180 degrees, r achieves its maximum value of a times 1 plus e. Then it shrinks back down as theta wraps around to 2 pi. That's what we expect. To find the equation, we start with the fact that at any point on the ellipse, the sum of distances to the foci is equal to the major axis length, 2a. We can write that as r plus r prime equals 2a, where r is the distance from the focus at the origin, and r prime is the distance to the other focus. But that's not such a convenient equation. We want it purely in terms of r and theta, not r prime. So how do we get rid of the r prime? We use the law of cosines. What's that? You don't remember the law of cosines? Don't worry, I do. The Pythagorean theorem says c squared is equal to a squared plus b squared, where a, b, and c are the lengths of the sides of a right triangle. The law of cosines is the generalization to any triangle. It says that for any triangle, c squared equals a squared plus b squared minus 2ab times the cosine of gamma, where gamma is the angle that's across from the c side. We'll apply that to this triangle with r prime as our c side. So we have r prime squared equals r squared plus 2ae squared minus 2r times 2ae times the cosine of what angle? It's the angle opposite r prime, which is pi minus theta. And the cosine of pi minus theta is minus the cosine of theta. Let's plug that in and do some algebra. At the end, we find r equals a times 1 minus e squared divided by 1 plus e cos theta. That's our equation. Now, as always, at the end of a long calculation, we need to ask, does it make sense? Let's see. When the eccentricity is 0, the equation reduces to r equals a times 1 over 1. That's just r equals a. That's a circle. Good. And when e is not 0, and we dial theta around the clock, cos theta goes from 1 to minus 1 and back to 1. So the denominator starts big and then gets small and then big again. That too makes sense. It says that r oscillates between a minimum value at theta equals 0 and a maximum at pi. In particular, if we plug in theta equals 0, we get a times 1 minus e squared over 1 plus e. And since 1 minus e squared is 1 plus e times 1 minus e, the 1 plus e's cancel out, and we're left with a times 1 minus e, which is what we expected. That's the minimum distance from the focus. Likewise, when theta equals pi, we get the expected maximum distance of a times 1 plus e. Okay, that's quite enough on the pure mathematics of ellipses. At last, it's time for astrophysics. What Kepler noticed, his first law, is that all the planets move on ellipses with the sun not at the center, but rather at one of the foci. Each planet has its own value for the semi-major axis and eccentricity. For the Earth, A is about 93 million miles or 150 million kilometers, or most conveniently, 1 AU. The Earth's orbital eccentricity is 0.017, quite small. All the planets in the solar system have small eccentricities. That's why it took so long to notice the orbits are not circles. Mercury has the most eccentric orbit with E of 0.21. Now, I can't resist telling you as a teaser, some of the planets around other stars, which have been discovered over the last few decades, have larger eccentricities, some even larger than 0.9. These incredibly elongated orbits were one of the big surprises of exoplanetary science, a topic of a future lecture. Any creatures on a planet with an orbital eccentricity of 0.9 would have alighted on Kepler's first law a lot sooner than we did here on the Earth. Kepler's second law is about how fast the planets move. When they're close to the sun, they move faster, in a specific way. As the planet moves, the line joining the planet and the star, the planet's radius vector, sweeps out area at a steady rate. In this animation, we're coloring in the area swept out by the radius vector and switching the color every second. When the planet is near the star, the radius is shorter. But the planet moves faster, so the colored sector has a large angular width. And when the planet is far away, the radius is longer, but the planet is slower, making a tall, skinny sector. What Kepler found is that all the sectors have the same area, equal areas in equal times. That's the way Kepler put it. But we know more math than Kepler did, so we can put it another way. Let's put the planet at an arbitrary position and watch it move for an infinitesimal time interval, dt. It sweeps out a thin sector spanning an angle d theta with an area dA. And what is the area of that sector? Well, the planet moves in both the radial direction, the r direction, and the perpendicular direction, which we'll call the theta direction, the direction of increasing theta. It's the motion in the theta direction that sweeps out area. Purely radial motion doesn't sweep any area. In time dt, the planet moves in the theta direction by an amount r times d theta, using the usual small angle approximation. So the swept out sector is basically a skinny right triangle with sides of r and r d theta. And the area of that triangle is 1/2 r times r d theta. That does leave out the tiny little corner piece of the sector with dimensions of dr and r d theta. That's the product of two tiny numbers. So in the limit of infinitesimal dt, that little piece is vanishingly small compared to the rest of the triangle. All of which means we can write dA equals 1/2 r times r d theta. And dA dt, the rate at which the area is swept out, is 1/2 times r squared d theta dt. If that rate is a constant, as Kepler observed, then d theta dt must be proportional to 1/r squared. That is the modern way to state Kepler's second law. Theta advances at a rate that varies as 1/r squared. Finally, there's Kepler's third law. This one is about the total time required to go all the way around, the orbital period. The bigger the orbit, the longer the period. To be quantitative, let's look at a logarithmic chart where the horizontal axis shows the semi-major axis in AU, and the vertical axis shows the period in Earth years. So the point representing the Earth is at 1 AU and 1 year, and the other points are for the other planets. It's really striking. They all fall on a single straight line. It has a slope of 3/2. If we move 2 units to the right, the line goes up 3 units. Since this is a log plot, that means that the log of p is 3/2 times the log of a, plus some constant, which in turn means that p is proportional to a to the 3/2 power. That's Kepler's third law. Another thing we know now that Kepler didn't know is that other planets themselves have orbiting bodies, moons. So let's add the data points for the 4 biggest moons of Jupiter. Look, they all lie on a straight line too, with the same slope of 3/2. But interestingly, it's not the same line as the one defined by the planets. It's shifted up to a longer period for a given semi-major axis. So we need to understand 2 things. Why is p proportional to a to the 3/2? And why do you get a larger proportionality constant for the moons of Jupiter? Before we answer that question, a quick recap. Kepler's first law, the orbits are ellipses with the sun at one focus. Kepler's second law, d theta dt is proportional to 1/r squared. And Kepler's third law, the orbital period, p, is proportional to a to the 3/2. It's important to keep in mind, these aren't really laws in the sense of the fundamental laws of physics. A better name would have been Kepler's patterns. Kepler didn't understand why these patterns hold. That task fell to Isaac Newton. Newton's law of motion is that the force acting on a body equals the mass of that body times its acceleration, F equals ma, or m dv dt. And Newton's law of gravity, as we saw a couple of lectures ago, is F equals minus g times big M times little m over r squared times r hat, where in this case the big M is the sun's mass and the little m is the planet's mass. So now let's roll up our sleeves and show how these laws relate to Kepler's laws. You might expect we'd go in order and start with Kepler's first law, but it turns out Kepler's second law is the most fundamental. So let's start there. The key concept is the conservation of angular momentum. Before getting to angular momentum, though, let's think a moment about momentum and velocity. Momentum is mass times velocity, P equals mv. And the velocity has two components. In a time dt, the velocity takes the planet from one position to another, changing both r and theta. That means the velocity has a radial component, toward or away from the origin, and an angular component in the perpendicular direction. The radial component, v sub r, is equal to dr dt. And the angular component is r d theta, the distance that's moved in the direction of increasing theta, divided by dt. So v theta is equal to r d theta dt. Angular momentum, which we'll write as L, is defined as r times mv theta. Only the angular component, the sideways component of the velocity, matters. And since v theta is r d theta dt, we can write L as m r squared d theta dt. In vector language, L equals r cross mv, the cross product being the way to pick out only the perpendicular component of a vector. It has a magnitude of r times the component of mv that's perpendicular to r. Why do we bother defining angular momentum? It's because in some circumstances, it's conserved. It doesn't change with time, even if the body's changing in lots of other ways. The classic example is the twirling figure skater who pulls in her arms, effectively reducing her r, which means her d theta dt must increase to compensate. That's why she twirls faster. Angular momentum is conserved whenever there is no net torque, no force in the theta direction, which is certainly true for the planets. The only force is gravity, which is in the radial direction, toward the sun. So, as a planet goes around, even though r and v are always changing, r squared d theta dt is a constant, and therefore d theta dt varies as 1 over r squared. That's Kepler's second law. Presto! So we now see Kepler's second law is a consequence of the conservation of angular momentum. Just as the ice skater twirls faster when she pulls in her arms, the planets twirl faster when they approach the sun. This is an important result with implications beyond planetary motion. It helps explain why material speeds up as it spirals into a black hole, why a star spins faster when it contracts in size, why a young star is surrounded by a spinning disk of material within which the planets are formed. I also want to make sure you noticed we never used the inverse square law of gravity to prove Kepler's second law. All we used was the fact that there's no net torque, so angular momentum is conserved. We would have obtained the same result for any so-called central force, a force in the radial direction that only depends on r and not theta. In some alternate universe where gravity goes like 1 over r cubed, the planets would still obey Kepler's second law. Onward then, to Kepler's third law. Why is the orbital period proportional to the 3/2 power of the semi-major axis? We're going to do this one in 2 stages. First, we'll prove it for a circular orbit, where we can see the physics very clearly. Then in the next lecture, we'll tidy up and prove Kepler's third law for the general case of elliptical orbits. Imagine a planet moving in a circle of radius a with some constant speed, v. Over a full orbital period, p, the planet travels all the way around the circle. Therefore, v must equal the circumference of the circle, 2 pi a, divided by p. Or equivalently, p equals 2 pi a over v. So we already see one reason why p increases with a. The circumference of the circle gets bigger. There's a longer way to go. In addition, as we'll show now, when a is larger, v is lower. The planet moves more slowly because the gravitational attraction is weaker. This increases p even more, so that at the end of the day, p goes like a to the 3/2. In a time dt, the planet advances by a small angle d theta, which corresponds to an arc length of a d theta. So v equals a d theta dt. During that same time interval, the velocity vector rotates by the same angle d theta. The change in the velocity vector is v times d theta. And so the magnitude of the acceleration, the rate of change of velocity, must be v d theta dt. We can combine the equations by solving the first one for d theta dt and then inserting the answer, v over a, into the second equation. That gives an acceleration of v squared over a. We've just proven something you might have already known. To keep a body moving at speed v in a circle of radius a, you need to supply an inward acceleration, a centripetal acceleration, of v squared over a. In the case of a planet, that acceleration is provided by the sun's gravitational force, g times big M over a squared. We set that equal to v squared over a, solve for v, finding v equals the square root of gm over a, which we can then insert into our earlier expression for the period, and presto, we see that p is proportional to a to the 3/2 power. We also see that the proportionality constant is 2 pi over the square root of gm. It goes down with the mass of the attracting body. That's why we saw a vertical offset between the data for the planets around the sun and for the moons around Jupiter. The Jovian moons have a longer period for a given A because Jupiter is less massive than the sun. So, not only do we understand Kepler's third law, we also see it's a useful way to measure the mass of the attracting body. Let's do that for Jupiter. First, though, let's rewrite Kepler's third law in a more convenient form, a so-called scaling relation. We know that when m equals 1 solar mass and a equals 1 AU, the period will come out to be a year. That's the situation for the Earth. And we also know that p is proportional to m to the minus 1/2 power and a to the 3/2 power. So we can rewrite Kepler's third law as p equals 1 year times m over m dot to the minus 1/2 times a over 1 AU to the 3/2 power. What we've done is evaluate the equation for a benchmark case, the Earth, and then specify how the answer scales with the inputs, m and a. That's a scaling relation. It's an alternate way to express Kepler's laws in terms of the most natural units for the context of planetary orbits. The original equation, with the 2 pi over root gm, is completely general. It works in any context with any consistent set of units, but it doesn't give us a sense of scale. The scaling relation is also handy because as long as we use units of years, AU, and solar masses, we won't have to look up the numerical values of g and the mass of the sun or worry about the 2 pi. We can just plug the numbers directly into the scaling relation. We can make a scaling relation out of just about any equation, and we often will, because it helps give us a sense of the numbers. It keeps us from getting lost in the orders of magnitude. Let's illustrate with Jupiter. We see from the chart that Europa has a P of 0.01 years. And the value of A is not quite 5 tick marks over from 0.001. It's about 0.0045 AU. If we plug in those numbers into the scaling relation and solve for m over m dot, we get 0.0009. We just learned that Jupiter is a bit less than 1,000th the mass of the Sun. Kepler's third law will be our faithful companion throughout this course. We just showed it holds for circular orbits. In the next lecture, we'll show it's also true for elliptical orbits. And then later, we'll upgrade it to handle the case of two objects of comparable mass orbiting each other instead of a tiny planet orbiting a much larger sun. Kepler's third law is the most reliable way we have to measure the mass of just about anything in astrophysics. The basic idea is that to measure an object's mass, we need to watch other things moving in response to its gravity. As we'll see, it works for stars, planets, black holes, neutron stars, entire galaxies, and even in a sense, for measuring the mass of the entire universe.